All right, so let's talk a little bit. We'll just intro into concavity in the second derivative test. So on this stuff, this moves us one step further. I would say this is something that this is going to be one of those things it pays to just try to get it in class, and then you can always re-get it later, right? But this takes a little thought. I mean, there's some mental brain twisters on this a little bit. So you got to really focus on what we're doing. And then once you get it, once the light bulb comes on, you can always get it to come on again. Okay, so a couple things here. This is a little bit wordy, but we need to agree on some definitions. So the second derivative, f double prime of x, is the rate of change of f prime of x. And we've talked about this before. Remember, we've done some stuff in the past. We've already sort of laid the framework for this discussion. Remember that stuff we did where I gave you a function and you had to graph the first and second sketches of the first and second derivative test? We did that a long time ago. You guys got pretty good at that, right? Okay, so we're going to go back to that a little bit. So it is the rate of change of the slope of the function with respect to x. That's what the second derivative really means, the rate of change of the slope. Now try to conceptualize that. So what does that mean then when the second derivative is positive? That means the slope of the function increases with increasing x. What's that going to look like? As I go further to the right, yeah, the slope is going to get steeper, right? Or it's going to get less negative. It starts negative. As I go further to the right, it gets less negative, which is the same thing as increasing, right? Okay, do you see that what that's going to do is that's going to give us a general overall shape that's going to be an upward concavity, right? The easy way to visualize whether it's an upward or downward concavity is to draw a tangent to the function. And if the function sits above the tangent line, that's defined as upward concavity. You can think about it as kind of catching water. If it rains on our function, if it's bowl-shaped up, that's concave up. It's going to tend to catch that water. Whereas if it's concave down, it's going to tend to shed the water as it rains on our function, right? Okay, so positive second derivative, the rate of change of the first derivative is positive. That's what we call upward concavity. And it literally, the shape of the graph is going to be concave upward, the overall shape, on those intervals where the second derivative is positive. When the second derivative is negative, the slope of the function is decreasing with increasing x. So we're going to be going from this, as I move to the right, it's going to tend to get more like that, right? Which results in a function that's going to be concave down. It's going to shed water, okay? So on intervals where the second derivative is negative, the function will have this downward concavity, okay? All right, so let's see, I built some stuff here to help you visualize this. Hopefully this helps. So let's just take a polynomial function for a second. Let's just take this guy. So there's my polynomial, x cubed minus x squared minus 6. I can move along that thing, and there's the coordinates of points on that function are going to change. Okay, let's do a couple things. Let's calculate, we're going to define g of x as the first derivative of f of x, and h of x as the second derivative, okay? So let me go ahead and add a vertical line here, just to help us keep track of where that point is, okay? And do I need that point? I don't really need that point, do I? What did I just do there? What's that do? Oh, no, never mind. Okay, I see what I got. Turn that off for a second. Okay, what if I graph the first derivative of this function? See if you can kind of tell me, remind yourselves, what's that going to look like, the first derivative? So where's the first zero of the first derivative function going to be? At roughly what value of x? It doesn't look like it's exact, but yeah, a little less than -1, little left of -1 it looks like, right? where's the next zero of the derivative going to be? Yeah, a little left of 2, where I get another horizontal tangent, right? Okay, good. Yeah, you're getting this. Okay, so there we go. Perfect. Okay. Now, if we differentiate that, where's the zero of the second derivative going to be? Yeah, something looks like it's going to be to the right of 0 a little bit, where the second derivative is equal to 0, where it has a horizontal tangent, right? Okay, so there it is. We can find that spot if we want to. It's at 1/3, it looks like. Okay. Now let's go back and so the second derivative is negative where? We're just focusing on the orange function now. Here, I'll get rid of the blue one. There's the second derivative is orange. To the left of 1/3. So all values of x less than 1/3, that's where the second derivative is negative. Values of x to the right of 1/3, so greater than 1/3 is where it's positive. So is that reflected in the shape of our function? Yeah, look at this. Do you notice here that that's about where this function transitions from being concave down to all of a sudden now it's concave up? Look where that's happening. It's happening right at 1/3. Okay, so we can make a parallel construction in our minds here of what critical numbers of the second derivative can do. Critical numbers of the first derivative are points of transition of slope, right? We're transitioning from positive slope to negative slope at that 0 of the first derivative. We're transitioning from negative slope to positive slope at this 0 of the first derivative, where we get horizontal tangents. Second derivative is where we're transitioning concavity. We're transitioning from downward negative concavity to upward positive concavity. Okay, the definition of that kind of a feature, topological feature, that's what we call an inflection point, where we're transitioning concavity. Okay, does that make sense? Okay, so if we, again, let's look at this point. Okay, if I scoot, notice now what I'm graphing here, the red point is just are the coordinates of the point on the function. The purple point up there, that's giving us the x value of the function, and the y coordinate is the concavity. It was is the second derivative, which quantifies the concavity, right? So notice that right about, well, I missed it, but it's right in there is where the concavity transitions, right? From positive to negative. And sure enough, that purple line right there, you can see that where it's hitting the red function, that's the inflection point. That's what's dividing it between concave down and concave up. Anybody see that? Okay, give me thumbs on that. Does that all make sense? Okay. All right, so there's one little tool. Now here's another one. What did this one do? I got to remember. Spent time building this. Oh, this was just another, yeah, okay, this is just another version, right? Just another function. Same kind of stuff, different function. Okay, so if we start off with f of x is just some polynomial. And I made this one pretty general, so we could choose the value of k, and we could choose what kind of polynomial, what degree polynomial. Well, if it's a second degree polynomial, it's just a parabola, right? Okay, the first derivative is, in this case, would everybody agree the first derivative is just going to be a positive constant? Everybody agree in this case? No, that's not true. First derivative is a sloping line, right? With a 0 at the point 0, 0, because that's where we have a horizontal tangent, right? That better? And it's negative to the left of that because the green function's decreasing, positive to the right because the green function's increasing uniformly, okay? The second derivative would be the derivative of the red function, which is the first derivative. Well, that's just a positive constant then, right? Because the first derivative is just a linear function with a positive slope, right? So there's our second derivative. So what's that tell us about the concavity of this parabola? It's upward everywhere, isn't it? Okay, it's upward everywhere. Okay, if I make this a cubic function, well, now that changes everything, right? Now the first derivative becomes quadratic, and the second derivative becomes linear with a non-constant linear. Okay, and now this one, would you agree? This one does have a point of inflection at 0, 0. That's where it changes from concave down to concave up. Okay, good. All right, so then here's the next issue. This can be confusing to people, and this is another one where sometimes this isn't always treated super well, where it can be confusing. But I'm going to make it very simple for you. Can you tell me why the top example, the blue example, is an inflection point, but the red example is not? That is not an inflection point. What's the difference between the two? They're both, what's similar about the two? They're both transitions of concavity, right? Because wouldn't you agree the blue function is concave up to the left of that point, concave down to the right? Same thing with the red function. But what's the difference? What disqualifies the bottom one from being an inflection point? There's no, and here's the quick test you can always apply. In order for a function to be an inflection point, it has to fulfill two criteria. It has to be a transition in second derivative, transition in concavity, and a tangent line has to exist at that point. So the derivative must be defined. Okay? If the first derivative is undefined, then that disqualifies it as a potential inflection point. Okay? Does that make sense? Okay, and that makes things a lot easier if you remember that rule. Okay, that's probably about where we're going to end, isn't it? Yeah, that's a good spot to end.